Before we can begin performing analysis on trusses, we need to be able to classify them so that we can know the proper tools and decisions to make in order to perform the analysis. We're going to focus on classification of 2D trusses or coplanar trusses. We're going to determine whether they are determinate, indeterminate, or unstable. And the key concepts we're going to use are classifying the trusses by comparing the number of reactive forces with the number of equations of equilibrium, and we're going to check for internal stability of the trusses. Here are the three trusses we're going to classify, and we're going to evaluate whether they're statically determinate, indeterminate, or unstable. If they're indeterminate, we're going to specify the degree of indeterminacy. Let's begin with the truss labeled A. This truss has pin supports at the bottom, so we get two force reactions at each of those joints. So my unknown support reactions is 4. Number of bars in the truss, 1, 2, 3, 4, 5, and then that's repeated. 10, 15, 16, 17, 18, 19, 20. How many joints? 1, 2, 4, 6, 8, 9, 10. 10 joints. The comparison we need to make is unknowns, which is R plus B, 4 plus 20, or 24 unknowns for this truss. Our equations, which is 2 times J, for 20. We subtract the number of equations from the number of unknowns, to find that it's 4 degrees indeterminate. Now we still need to check internal stability. Every shape in this truss is a triangle. Therefore, it's internally stable. And our assessment of 4th degree indeterminate stands. Okay, our next truss. We have pin support here, which gives us 2 reaction forces. A roller here, which will give us 1. So my unknown support reactions is 3. A number of bars or elements in the truss. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the number of joints. 1, 2, 3, 4, 5, 6, 7, 8. Again, we'll compare our unknowns, which is R plus B, 16. My number of equations, which is 2 times the number of joints, which is 16. Subtract my number of equations from my number of unknowns, 0, which implies statically determinate. Once again, I need to check internal stability. And again, all the shapes inside this truss are triangles. Therefore, it checks. It is determinate. Our third truss. We have a roller support here, 1 vertical reaction. A roller support here, another vertical reaction. So we probably already see that there's a difficulty, but let's go through our process and see what else we discover. So our unknown support reactions are 2. A number of bars or elements in the truss. 1, 2, 3, 4, 5, 6, 7, 8, 9. Number of joints in the truss. 2, 4, 6. So my unknowns R plus B, 2 plus 9, for a total of 11. My equations are 2 times J, or 2 times 6, 12. I subtract the equations from the unknowns, and I get a negative 1, which is less than 0. Therefore, it's unstable. Now notice, all our reactions are parallel. Therefore, it is externally unstable. If the wind blows from the side or somebody runs into it with a piece of equipment, it slides to the side. Also, there's a region that is not made of triangles. That region is right in there. That means it's internally unstable. So our assessment of unstable is demonstrated externally and internally. Let's see what we learn. The first truss we discovered was indeterminate because the number of unknowns exceeded the number of equations of equilibrium, and it exceeded it by 4, so it's 4 degrees indeterminate. Our next truss, the number of unknowns matched the number of equations of equilibrium. It's determinate. And our last one we found to be unstable. And in that case, the number of equations of equilibrium exceeded the unknowns. We found that it had parallel reactions, which makes it externally unstable. And we found that it has a region not made of triangles, so it is also internally unstable. Now with this information, we could then decide how do we proceed for structural analysis of these trusses.